Hexagon is white pentagons set upon the task of trying to determine which of the regular polygons do not have an integer interior angle measure for an angle. Okay, your wife explains it to you very slowly, but you're still kind of confused. So she starts to write some formulas down. She tweaks with the controls of the note that Equi has given you, and she kind of breaks it down step by step. Okay, she says the sum of the interior angles of the first regular polygon you know about, the equilateral triangle, has an interior angle sum of 180. And if you have a regular polygon, you know all the angles are equal. So the measure of one of those interior angles would be 60 degrees. She tries to expand on the idea and gives you a formula. She says the interior angle sum of any polygon is n minus 2 times 180, which is equal to 180n minus 360. She took the time and she's very patient with you, and she explained why the n minus 2 exists, and she explained why the minus 360 exists. Okay? After you look at the first regular polygon's interior angle, she starts to show you some of the others that at least Equi's note would help. She pauses for a little while on heptagon because heptagon is her daughter and she's missing still. Okay? Gets to octagon, goes to nonagon, decagon is where this particular note that the town elder Equi gave you to investigate this scenario. Okay? She has an epiphany and she says, I think I know the answer. Okay? The real difficulty with the answer is not with the interior angle, but with the exterior angle. And with that, she fiddles with the controls a little bit. She does a little bit of typing. And she can see that the real key to this problem is the exterior angle. She knows, as most people do, all the exterior angles are going to add to 360 degrees. So if you divide, because this is a regular polygon, if you divide 360 by n, you get the exterior angle as 180. Now, this isn't to say that you couldn't have found it by finding first the 60 interior and finding the supplement. Both of them get you to the same place. Okay? The measure of one of the interior angles can be found either by finding the supplement of the exterior angle or by finding the total interior angle sum and dividing by n because each one of them is n. Okay, in the case of the equilateral triangle, the measure of one interior angle would be 60. Okay, if we continue to look up, even though they don't touch, because the regular polygons have all equal angles and all equal sides, that every place that you draw an angle could be by the one that you're talking about. Okay, so we get to pentagon, and it starts to make sense to hexagon. Hexagon sees his familiar interior angle and assumes that 60 could be drawn anywhere. And then your wife once again pauses when she gets to the heptagon because she misses her daughter deeply. Okay, she continues on. You go through an octagon, you go through a nonagon, you go through a decagon. All of those are supplementary on the interior and exterior. All of them have an integer interior angle. Okay? She's not very happy right now with that because this is basically a trick question. It's impossible to list all of the regular polygons that do not have an integer interior angle, because if that means that you can have n equals any number of sides. But as n becomes extremely large, you can see your shape is becoming more and more circular. But there is a maximum if you have an integer as a constraint on your interior angle. Okay, the largest interior angle that you could possibly have and still have a polygon would be 179 degrees. This does not mean that there's not polygons out there that are bigger than a 360gon, because that's how you get the idea of 179 degrees on the inside. That's just to say that if you're restricting it to integers as the interior angle measure, that you only would have up through 179 in your interior angle. Okay, You're still a little bit confused, so you ask her to explain it to you one more time. She flips the note over, and on the back she starts writing some numbers. She says 360 has a prime factorization of 2 to the third power, 3 to the second power, and times 5. Okay, which means it has a great deal of factors and factor pairs, but those are still finite. Okay, um, you can see the list: 1 in 360, 2 in 180, 3 in 120, 4 in 90, so on and so forth until you get 18 and 20. You know, once you get numbers that are relatively close to each other, you've probably exhausted all the possibilities of having integer factor pairs. Okay, so this is where it became a trick question. Your wife explains to you very clearly that Equi gave you a question that really did not have an easy way to directly answer. So you have to kind of look at this from a perspective that you can only explain the ones that do have integer answers, and then you can say that all the rest of them do not work. Now, she's not going to formally prove this, but she's going to basically talk us through it. Okay, these are the factor pairs of 360 in their full glory. Okay, the smallest integer interior angle is 60. That's what happens when you have the smallest number of sides that actually creates a regular polygon. The smallest number of sides that creates a regular polygon is 3. Okay, if we think about the largest integer interior angle that could possibly exist would be 179 degrees. That 179 degrees comes from a 360gon, or a 360gon. I guess I could say the Latin version of it, but nobody would understand it and nobody would care. Okay, typically in math you say probably through the first 10 for the first 10 or so sides, and then you don't care. If you look at it directly, there are 22 different usable multiples or factors of 360 that help you find integer interior angles. Okay? Obviously, the first ones that we looked at were easy to see. I probably wouldn't use anything beyond decagon. I use dodecagon occasionally, but the rest of them, it's pretty fancy vocab, really dependent on some Latin, and there's disagreement even between the people who are mathematicians about how you really say certain words. So I probably would have stopped writing anything but an n-gon after about the 10th side. Okay, because the 11 they have a disagreement about what the name of it is. It's horribly spelled. 12, most people have seen dodecagon at some point. Pentadecagon, that's one that, you might get. Penta meaning 5, decagon meaning 10. 5 plus 10 gives you 15. Octadecagon does some of the same thing. Isosagon, I guess, or icagon, depending on who you ask, is a 20-sided polygon. There are ways to name the rest of them using fancy Latin-based terms. I would not waste my time, beyond the decagon. I don't expect people to know more beyond the decagon. Okay, you go through this and you find out there are basically 22 regular polygons that will have an integer interior angle, but it's difficult to say how many do not. So you can basically say all regular polygons except these 22 have non-integer interior angles. Okay? Your wife, longing for your daughter, goes back and says, she's the only one of the ones we looked at that doesn't have an interior angle or didn't have an interior angle that's an integer. She sighs deeply. Equi exclaims, well, this is the key to what she was asking me questions about. She wasn't feeling like she belonged in your family, because if you look at it, in your family, there's your father, the father, Hexagon, he's got a nice interior angle sum. There's a mother, pentagon, he's got a nice interior angle sum that leads to a nice integer. She's got a nice interior angle sum that leads to a nice interior angle. Hexagon has a nice interior angle sum that leads to a nice interior angle. Even the family pet, pentadecagon, has a nice interior angle sum, which leads to a nice interior angle. Okay? Notice, heptagon's not on the list. And this is the key. Equi said when she came to him, she had long conversation about math with him. And then they got into the discussion about interior angle sums, and she found out that she was the only one in her family that did not have an interior angle. And this bothered her tremendously. How could that happen? My mother's has an integer interior angle. My father has an interior integer angle. Okay? So why don't I? Eki tried to explain the same thing his mother explained to her, but she just wouldn't hear it. So this led me to try to discuss the Great Triangle Wars to her to get her mind off the fact that she did not have an interior angle sum or interior angle measure that was nice. She's got one that's not so nice. Okay? And that is what led her to be more excited than I could possibly believe. She had to know about these triangle wars. She just had to. She thought it was the key to the mystery of why. Equi tried to explain it to her was really just because one of her number of sides just didn't go unevenly into 360. But the discussion that I led up to that basically made her force me to let her go to one of these islands to investigate farther was the fact that I said that there was a triangle rebellion at some point. So she just had to know about that triangle rebellion, where equilateral and isosceles and right triangles and all the rest of the triangles basically had a battle for control. This is what led us to separate ourselves. Some would say we've classified ourselves.